This video lesson is about RC circuits. RC circuits are circuits with a resistor, that's the R part, and a capacitor, that's the C part. Like this. It turns out an RC circuit like the one I've just drawn is super boring. There's not much that's going to happen here because when we draw the capacitor, we draw it with this gap in between the two plates. That's not just a style choice, that represents something physical about what's happening at the capacitor. There's no electrical connection from one plate to the other, there's a gap here, which means this circuit is not actually a closed circuit, it's an open circuit. And when it just sits here like this, we don't actually expect charge to flow. So these circuits need something dynamic to happen in order for them to be interesting or worth talking about. And that dynamic thing that's going to happen is going to happen when we open or close a switch. So here's a drawing of an RC circuit with a switch. This switch is in the open position because the end of the switch is not actually touching this wire terminal. We're going to imagine that we're beginning with a charged up capacitor. So this capacitor actually has some amount of charge on it, plus Q and minus Q, so that it has a potential difference across it. In this sense, it's a little bit like a battery. A battery has an EMF, which is a potential difference. The capacitor is going to begin with a potential difference, but the difference between a capacitor and a battery is that the battery maintains a constant potential difference. The capacitor's potential difference is going to begin to change the moment we close the switch. As soon as the switch is closed, the charge on the capacitor is going to begin to flow. If we imagine the top plate is positive and the bottom plate is negative, then we visualize current as positive charges moving away from the positive plate and attracted toward the negative plate. So that would produce a downward current through my resistor. The capacitor begins fully charged and then discharges so that it asymptotically approaches zero. This is an exponential decrease. Because of the relationship of capacitance to charge and voltage, if charge decreases, the voltage has to decrease by exactly the same amount so that the ratio is constant, and that's the value of the capacitor. So the voltage versus time curve is going to have exactly the same shape as the charge versus time curve. Furthermore, a flow of charge with time, the charge decreasing represents a flow. This is the same thing as current. We can write equations to describe both of these exponential decreases. They have exactly the same form. The current in the circuit as time goes on equals the initial current in the circuit times E, that's Euler's number, you can find it on your calculator, raised to the power of negative T for time divided by RC. Both R, the resistance, and C, the capacitance, are in the denominator of this exponent. The same form of the equation shows up for voltage, that the voltage across the capacitor over time depends on the voltage you start with, times E, Euler's number, raised to negative time divided by RC. And again, RC, both of those are in the denominator of that exponent. Just a reminder, Ohm's law always applies to the resistor. So the voltage at any given time equals the current through the resistor times the resistance. And I mean the voltage across the resistor is equal to the current through the resistor times the resistance. So let's take a look at charging a capacitor, how you get charge on this capacitor to begin with. In order to charge a capacitor in an RC circuit, you need some initial source of voltage that's going to push charge onto your capacitor. So we will use a battery for that. Then you also need a capacitor and you also need a resistor, and we're going to connect everything with wires, and we'll include a switch so that we can decide when we want to start charging this capacitor and when we'd like to stop charging the capacitor. Once we close the switch on our circuit and begin to charge up the capacitor, charge gets pushed by the battery toward the capacitor, and we begin to see charges accumulating on the capacitor. So in the graph of charge versus time, we begin at 0, and then the push begins, and we put more and more charge on the capacitor. The amount of charge that we put on the capacitor approaches a maximum value. It approaches it asymptotically. It never actually reaches that maximum value. It just gets slightly closer and slightly closer. Similarly, the voltage across the capacitor begins at 0 when the switch is open, and then as soon as the switch closes, it increases and asymptotically approaches the value equal to the EMF of the battery. It will never actually reach the EMF of the battery, but in practical terms, it will get so close that a voltmeter couldn't tell the difference if you wait a long time. Now, if we think about current, this is kind of interesting. Current is related to the change in the charge. So when the charge is changing rapidly, that's a big flow of charges. That's not a minimum current, that is a maximum current. And then when the charge changes less quickly, it has a shallower slope, that's going to represent a smaller current. So the current versus time curve for a charging capacitor looks like an exponential decrease, just like it did for a discharging capacitor. So the current is going to be equal to some initial current times E, Euler's number, raised to the negative T over RC, just like it was for the discharging capacitor. This is different from the voltage. The voltage has a different relationship, and that's going to show up mathematically in its equation. The equation for the voltage across the capacitor equals the EMF of the battery times this quantity of 1 minus e to the negative t over RC. We begin at time equals 0. E to the 0 power is 1. So 1 minus 1 tells us that the initial potential across the capacitor is equal to 0. And then it will increase from there, asymptotically approaching this value equal to the EMF of the battery. So those are all of the equations and the explanation behind them that you will need to use to analyze RC circuits.